I will go to the next topic. So, I want to talk about the topological decomposition of hyperbolics to fall into elementary orbifolds using geodesic one orbifold. Sigma is a compact hyperbolic orbifold with the negative order characteristic and has a geodesic boundary. So boundary could be one orbifold or a cross circle, right? So if you have any set of mutually disjoint collection of um, simple cross curve or one orbifold, so that so you remove these, and then so each component, you look at each component and then you complete it with respect to something like Cauchy completion, and then see that the orbifold order characteristic is all negative. So suppose we can do that. Then we can isotopy to these two geodesic or geodesic full orbifold, so that they are also mutually disjoint. Okay, so this is not so completely trivial actually, right? Please see my book. I mean my paper with Goldman, and then see how I proved it. Uh, so of course you can do this. Okay. Yeah. So because of this construction, so whenever you have some hyperbolic structure, you can cut it up so that along geodesics or cross geodesic or geodesic full orbifold, so that the remainder has some orbifold of negative order characteristic if you complete it, and but you can do this until some finitely many times. So these will be the elementary ones. So you cannot further decompose, okay, after this. So first one is a pair of pants. So pair of pants is actually topologically it's the smallest sort of surface, because you cannot cut off anymore, because if you use any more simple coarse curve, then it will bound some sort of annulus with the boundary component. Okay, so the way to see it is because pair of pants is a disk with two punctures topologically. So any simple cross curve will bound some sort of a disk with two punctures or one punctures or no punctures, right? So therefore, if you bound two punctures, it will be parallel to the it will be isotopic to the boundary, the other boundary. And then if you just have bound just one component, one puncture, then it will be parallel to homotopic to that curve. So it will bound an annulus. So you cannot do this any further. So you cannot divide it so that you get a negative Euler characteristic in the complement. Okay, in every component, right? Every component of the complement has to be negative Euler characteristic. Has to have a negative Euler characteristic number. Right. So pair of pants is elementary. Okay, so that's for a topological sense also. And then the next one is annulus with one point of order n. So it's written like this. So cone point. So this semicolon means that this will be the corner reflector, n will be the cone point. So after this. So this is a disk, and then there's I mean, this is the annulus. A means the annulus, and then there's some one cone point in the inside. Okay, and so it will have two boundary components, right? And then the next one is a disk with two cone points of order PQ, which is greater than 2. So it will have a two cone point. So you have a disk with two cone points inside, and then one of them has to be bigger than 2. So if it's both 2, then it has order characteristic 0. So that's why you can do that. So D means the disk. Okay. And PQ means after the semicolon means it's the cone points. And the sphere with 3 cone points of order PQR. So when the 1 divided by P plus 1 divided by Q plus 1 divided by R is less than 1. Okay, so you write S2 PQR. So S2 means the sphere. So those are the three most important ones. And then the next one is an so maybe we should see the picture first, right? So these yeah. So these will be pair pans and then one annulus, one cone point, 2 point points. So this is P1, P2, P3, P4. Okay, and so now we have an annulus with the one boundary component union of a singular segment and the one boundary orbifold. So it's two-pronged crown, or so at the one boundary component is a union of one mirror points and then one just boundary for one orbifold. So it's a union of these two, and the other one is just a cross circle. So in the so you can think of, if you fully mirror everything in the one boundary component, you get that corner reflectors of order 2, 2. So you get annulus with corner reflectors 2, 2, and no cone points here. So we call the two-pronged crown. So it looks like two-pronged crown, right? So okay, so that's a name of given by Thurston, and so the point here is that you have to fully sever one boundary component, but without the being severed, you still call it 2, 2. But so the names usually when you sever everything. So it has two corner reflectors or the two if the boundary component is severed, and the other case is annulus with one boundary component, singular order of locus with one corner reflector of order n bigger than equal to 2. So it has just now it's just union of one mirrored silver point, but there's one corner reflector with some order n bigger than equal to n, bigger than equal to 2. So that's called A2. I mean AN with the semicolon empty, and then the A2, A3 is a disk with one singular segment and one boundary orbifold, and the cone points of order greater than equal to 3. So this is like so yeah, you have a disk like this with two boundary components. So one is a silver, and then one is a boundary one orbifold, and there's a one cone point in the interior. So at the boundary there, you can, if you separate two of them, then you get a 2 corner reflector. And the disk with the one corner reflectors of order m and the cone point of order n, so that 1/2m plus 1 divided by n is 1/2 with no boundary orbifold. So this is when you have a disk with one cone point in order n, and then one corner reflector of order m at the boundary. So it will just be one singular segment. Okay. Okay. So those are so if you look at it, so there's an annulus with the 2, 2 here, and then nothing else, and then so there's some corner reflector here, and these are all silvered, and then this is silvered. So dotted line are the boundary, but anyway, so if you separate, then you get 2, 2 here, and then there's one corner reflector, and this one you get this with one cone point, and then this has some order here, higher than equal to 2, right? Okay, okay, and then there's a disk. So disk with the 3 edges and 3 boundary, 1 orbifold. Okay, so or if you separate, then it's like a hexagon. So you have 6 sides, and all of the things are all boundary. Every singularities are just corner reflectors. Okay. Or if you not separate, then there should be 3 of them which are not adjacent. Okay, and or 3 of them are separate and 3 of them are not separate. So this will be occur like jumping from one to the other type, right? And then there's a disk with 3 edges and 2 boundary on orbifolds. So three silvered edge. So this is a pentagon, and then 3 of them are silvered, and then two of them are not silvered. So boundary orbifold, and so 2 boundary ones are not adjacent. 2 edges meet at the corner of reflector and other end, and the remaining one is just a segment. A silver segment is called the pentagon. So if you silver everything, you get a pentagon with order 2 to n, right? So n is at one vertex, and the all other ones are 2, and then this, right? Okay, so if you see the picture, so it'll be like this. So this is silver, and then these are a boundary or force, okay? And then and D2 is right. And next one is a quadrilateral. So you have a disk with the 2 corner points of reflectors, or the PQ. So one of has to be bigger than equal to 3, and then the one boundary over 4. So the singular locus of a disk is a union of 3 edges and 2 corner reflectors. Okay, so this is called the quadrilateral. Okay, so it has PQ will be these 2, and then there's just one boundary for orbifold. So if you silver everything, then you get 2 here, right? So that's the quadrilateral, and then this with the 3 corner reflectors of the PQR, where 1 divided by P and 1 divided by Q. R is less than 1, and 3 edges. So this you call this a triangle, or T2 PQR. So PQR is, so this is the last one. Okay, so these are all the elementary orbifolds. Okay, so we of course have to prove that these are elementary. How do we prove that? So it's very similar to the Parapans case. So if you look at these again, if you have any simple closed curve, then it will bound the disk, and if this contains these 2, then you see that the circle is parallel to the the boundary, and this circle will bound an annulus, and so on. Okay, so those are the same arguments. So these are all application of Jordan curve theorem, right? And then for here, of course, then of course you need to probably do the full one for boundary as well. But so if you are not doing the silvering, then there is really no problem. And so even if you silver it, you can just take the neighborhood and get a right. So you cannot do anything further without destroying the orbifold by full one orbifold here. Okay, so or error right. So if you say these are boundary, then there's nothing more you can do. And these are boundary. So for these, I guess if you have so you call these boundary, then there is so you have to also consider full boundary for orbifold, like ending from here to here. And so the point is that so for example, this one is actually double covered in the orbifold sense by just the G2 action, like flipping these 2, and then this one again the same. You have G2 action like this. So fixing this, some arc, passing this, and then so there's some arc fixing this again cover, and then this one you can also do the same thing, like G2 action will cover this. And then here actually there's another G2 action. For this one, you can fix 3 arcs and then flip these, and then quotient is this one. And then for this one, you again do 3 arcs. 1 arc passes ending here, and then here, and then here, and then you get the covering. And then here you get another 3 arcs, like passing this way, and then you get this. And then, so you get three arcs like this, and then you get this. Okay. So if you have any boundary for orbifold, you can lift by the double cover to a simple cross curve here, and then you see that by the same reason you cannot do anything here. Okay, so that's why these are all the elementary ones. So you cannot do anything any more decomposition. Okay, so that's the proof for the elementary orbifolds. Okay, so basically, we'll do is that we take some compact hyperbolic orbifold with the negative order characteristics and the geodesic boundary, and then there exists a mutually disjoint collection of simple cross geodesic or mirror or cone or mixed type geodesic one orbifold, so that you can decompose to union of elementary orbifolds or some elementary orbifold with some boundary one orbifold cell, but additionally, okay. So those are the only possibilities. Okay, so you can show that, and then after that, you can prove that the Thurston's theorem that the hyperbolic RP2 structure on maybe this should be dropped. Sorry. Is homeomorphic to set of dimension like this, where K is the number of cone points and L is the number of corner reflectors and N is the number of boundary for orbifold. Okay. Okay, so I will do that next time. So I will end the lecture here today.